Hello, Kidney Warriors. James here from Dadvice TV, your online kidney health coach. And this is Dadvice TV Live. And boy, do we have a hot topic to discuss tonight. There's always been a need for kidneys and getting on these long lists for kidney transplants. And once I was diagnosed, one of the first things I heard about that I was very hopeful about was the implantable artificial kidney. Well, we have with us live tonight Dr. Shuvo Roy from the University of California, San Francisco. He is in charge of developing that thing, and we're going to talk about it. Hey there, Dr. Roy. How you doing?
I am good. Thank you. It's a pleasure to be with you.
Awesome. Now, can you tell us a little bit about your background for those that, maybe aren't like me and are super nerdy and are familiar with you?
Sure. First of all, thank you for having me on this program. And I'm excited to see all the messages that are coming and the viewers that are watching us today. So I am a professor at the University of California, San Francisco in the Department of Bioengineering and Therapeutic Sciences. And my background is an engineer. So I trained to make electronics and tiny sensors. But about 20 years ago, I got very interested in applying the technology to the medical needs. And over that time period, I have retrained or have become more familiar with medical devices. So today, I focus most of my effort developing medical devices in this area for kidney patients.
Awesome. And we are so appreciative that you made this change in your life to go this direction, because this is something we are so excited about in the kidney community. Now, I want to start at the beginning. What is the Kidney Project and what role do you play in it?
Sure, I'm happy to answer that. So, the Kidney Project is a national research and development effort to create a surgically implantable bioartificial kidney to treat those patients that don't have functioning kidneys, meaning those patients that are currently on dialysis.
Yep.
Our goal is to give kidney failure patients a much brighter future than dialysis currently affords, and to address the shortage of donor organs with a device that provides the healthy kidney's main functions without requiring immunosuppression. In my role on the
Mm-hmm.
Kidney Project, I am the technical director, which means I oversee the engineering development effort of the device. My colleague, Dr. William Fizel, is at the Vanderbilt University Medical Center in Nashville, Tennessee, and he is the medical director. He's a nephrologist, and he and I have worked for almost 20 years to move this project from a concept on paper and in his mind to something that's on the verge of moving forward at some point to clinical trials.
Awesome. So how does this bioartificial kidney work?
Sure. So the bioartificial kidney will be the size of a coffee cup or so, and it's a device that will be surgically implanted in the abdomen. And this device consists of two main components that work together to remove wastes from blood and provide the other functions of a kidney. These two components are, I call the hemofilter for
Mm-hmm.
removal of toxins from blood, and the bioreactor to provide the other biological functions of a natural kidney. The hemofilter filters toxins from the blood, separating them into a watery liquid we call ultrafiltrate, same as our kidneys do, that also contain some salts and glucose and whatnot.
Hmm.
Next, this watery ultrafiltrate is processed by the bioreactor, which has kidney cells, and sends much of the sugars and salts back into the blood, performing the reabsorption function of the natural kidney. And the remaining waste products and excess water are then concentrated into urine and directed into the bladder.
So it sounds like it practically works like a real kidney, creating urine with the waste. Is that correct?
Well, yes, in some ways, absolutely, it tries to mimic that. So the Bioartificial's kidney filtration system, the hemofilter, is constructed from silicon membranes with
Mhm.
precisely sized nanoscale pores, holes, if you will, like in a filter. These silicon nanopore membranes, as we call them, can process blood and ultrafiltrate much more efficiently than conventional polymer membranes. And the high efficiency of these membranes allows the device to be small enough to implant. And this efficiency also means the device can be powered with the body's own blood pressure. So it does not require any batteries or external power source.
That right there is awesome, because I know that was one of the challenges, was how to power this device. Approximately how big is it since it can be implanted?
So we can envision, just the efficiency of the membranes allows us to think of, typical dialyzer membranes, as you may have seen, is
Mhm.
yay long
Yes,
and
yes.
maybe this big. This will be the size of your fist or smaller. And moreover, because we're using silicon membranes that we have optimized with a special coating that prevents blood clots and prevents the accumulation of debris, we expect the filter should not need to be cleaned. And we are designing the device to last as long as possible. Obviously, that's yet to be seen, but we think based on the engineering work and the science that we know, it should last several years.
Awesome. And then if it does need some type of maintenance, like cleaning, is that another big surgery, or would that possibly be something more simple?
Well, as the engineer, you always have to think about anything that's engineered has the possibility to fail.
Mm-hmm.
So, what we as engineers do is to think about designing for life cycle management. What does that mean? So, we believe that if there's a failure, one could go to the doctor's office or the hospital and then get their filters replaced or the cells refreshed via some minimally invasive surgical technique. So it's not that major surgery that one would expect in the initial implant case, or you'd associate, say, for example, with a transplant.
Yeah. Now you mentioned there are some living cells in it, one part of it. Where do those cells come from?
Yes, so to mimic the function of a kidney, you can obviously use sort of completely synthetic elements, or you can use cells. We have taken a hybrid approach where the mechanical filtration unit is engineered, basically constructed in a factory, in a machine shop, if you will, but for semiconductors,
Mm-hmm.
semiconductor clean rooms. So there's no cells in that. For the second part, which provides many of the biological functions of a kidney that allows for blood pressure control, for example, vitamin D production, we felt that it would be too hard to replicate nature, and rather what we did was we used kidney cells, and right now we are using cells from human cadaver kidneys that are not of sufficiently high enough quality for transplant. We take those cells, find the good ones with my colleagues, and then use those in the device. Of course, long term, we are also researching other possible sources. So, for example, stem cells,
Mm-hmm.
or even one can think very sort of in the future, and maybe even possibly animal cells that you can edit the genes as to avoid all the challenges associated with animal cells and put them in our device.
Awesome. And you mentioned earlier you would not need immunosuppressive drugs. That's correct?
So yes, so one of the features of our device is this membranes that we have developed have the properties that they have these pores, these holes that
Mm-hmm.
allow wastes, but also allow nutrients to go through, but do not allow larger biological components such as immune system components, such as cells. So inside our bioreactor are these transplanted kidney cells, and they're separated from the patient by the silicon membrane. So the silicon membrane allows blood to be filtered, allows the salts and the waste to go through, but they do not allow the immune components from recognizing or interacting with the cells directly. And what that means is that as far as the body is concerned, they cannot kill them off, and so there's no need for immunosuppression. So this is one of the big benefits of the bioartificial kidney, in that the membranes that enclose the kidney cells also isolate them from the patient's immune system, and this avoids the need for any immunosuppression drugs.
Wow, that'll save so much money. And a lot of, I've heard stories of people who get a transplant and years later they have difficulty affording that medication, immunosuppressive. And it's kind of heartbreaking that a kidney could be lost because of that. So that is fantastic that they
So
won't need that.
let me add to that. You bring up a
Sure.
very important point, and I know that some of the listening audience is familiar with some of the advocacy that's going on. That's
Hmm.
actually something we need to change. So today, you get on dialysis, Medicare will pay for dialysis along with your private insurance.
Yep.
If you're on Medicare though, and you get a transplant, you get immunosuppression drug coverage for 3 years. So imagine that. So you've got a transplant, you're fortunate, you've won the lottery, but then you
Yeah.
lose the ability to pay for drugs. Um, so that many people basically are challenged by that. So there's
Hmm.
actually today, as we speak, there's advocacy going on at the Congress level to make sure that immunosuppression drug coverage is provided. So I encourage your audience and others to certainly support that.
Yes, certainly. Anything that can help us. Now, this artificial kidney, since it has real kidney cells in it, along with the kind of the mechanical part, will it replace all of the function of the kidneys, like taking care of my blood pressure, my phosphorus, my potassium levels, etc.?
So we envision that ultimately the device, the bioartificial kidney, will provide all the key functions of a healthy kidney. But to start, the initial version of the device will replicate the kidney's filtration and electrolyte balancing functions to start, because this will allow them to avoid dialysis, will allow them to be able to eat and drink more freely. So, for
Hmm.
example, patients will likely not need any phosphorus binders or drugs to treat hypotension. Many people go in for dialysis and their blood pressure drops because you're trying to jam this, what is supposed to be 24/7 cleaning
Hmm.
process, into
And in just a
3 hours,
handful of
right?
hours.
Yes. And so we think that, by doing the first version, by doing the the filtration function continuously, we'll be able to avoid the need for drugs to increase the blood pressure after dialysis, as is the case. But I should be clear, at the very first stage, I think we will still require the patients to do EPO because we're not providing that in this first version. And the dose, from what we think, will be likely less than what dialysis patients currently require. But nonetheless, the initial version will provide what I call 30% function, 30, so 25 to 30 milliliters of GFR, as your
Mm-hmm.
audience may know those terms. What
Oh,
that
they
basically
do.
means is that, yeah, they will not have to go on dialysis. It will allow them to live a more normal life, if you will.
Mm-hmm.
But as we refine the device, we'll increase that later.
Now, I let me tell you, the questions are going. People are asking the same question, and I'll be getting to it. You know which one they're asking for. But before we get there, who is the likely candidate for this device? Since it's going to give a certain amount of GFR, about 20 to 30 GFR, who is the candidate for it?
Sure. So, the, first of all, let's be clear. The bioartificial kidney will require an implantation surgery.
Mhm.
So that means that right off the bat, you have to be able to undergo anesthesia, for example, right?
Yeah.
So the initial clinical trials, we believe, will be open to dialysis patients that have been at least examined for transplant. They may even be on the transplant wait list because that means they have gotten a certain level of health that would allow them to undergo surgery. The specifics of age, body mass index and other restrictions will be worked out closer to the time of the trials based on the input from the institutional review boards and the FDA. And although the first trials will be initially in a narrower population,
Mm-hmm.
as the device is shown to be safe and effective, we'll work to make it available to all the patients that could benefit from it.
Awesome. And are there any types of kidney disease that this is better for, or it's not a good solution for? Or does it work for all types of kidney disease?
Well, again, I'll speak as the engineer, not as the nephrologist, but I think the point is this is a device that will provide kidney function and it will replicate at least some of the key functions of a kidney. So whether you have PKD, FSGS, diabetic nephropathy, I would imagine those would not automatically exclude you from it. I think the key criteria would be maybe specifics of your individual health, is what's going to determine that. But clearly, as we learn more and from the tests that we do, we'll be able to provide more information on that.
Yep. And you mentioned that with this device, it'll give you a GFR of around 20 to 30. Um, for those that are listening, I understand why that's important, but can you explain why that range is important?
Sure. So let's first of all say to everybody who may or may not have known what GFR is, glomerular filtration rate. It's a measure of how good your kidneys are. Healthy people have a number that's close to 100, and then we know about CKD1 and the different stages, CKD2, CKD3, CKD4, CKD5 being you need to be on dialysis or get a transplant. So you don't usually get to the end stage kidney failure or CKD5 until your GFR is around 10 to 15. That's when they say, hey guys, you got to get a transplant or you got to go on dialysis, right?
Yep.
As we all know, there's until you get to that point, you can live a more or less full life. And there are people who actually don't even know they have bad issues until they go to GFR and they go of 10 and 15 and they go, oh my gosh, I didn't even know. I just felt bad, but I was doing everything.
That was me. I didn't know until I got sick for about 2 weeks, end up in the ICU, GFR 8.
Oh my goodness. Yeah, exactly. Exactly. So we know our kidneys are very redundant. And if we can provide a level of GFR that's beyond dialysis, they can do many of the daily living activities.
Mm-hmm.
We also know when you look at just from a clinical perspective, people's health really go bad once they get on dialysis, right? I mean,
Mm-hmm.
before dialysis, there's a level of health. It's almost like you're okay, you're okay. Then you go to dialysis, your health really goes down.
Yeah.
So in some ways, we said, okay, how can we push them back up that curve? And so we targeted initially a GFR in the 20 to 30 milliliters range because that level provides a substantial therapeutic benefit
Hmm.
while being achievable with the technology in the fastest amount of time. It will allow the patient to remain free from dialysis, make the adjustments like you did, probably with
Hmm.
health and any other medications, and maintain a meaningful quality of normal life.
Yeah.
And I hope that with time, as we refine the technology, we'll definitely bring that level higher.
Yeah. For me, once I got around GFR 24, 26 somewhere, I was able to manage all of my symptoms and my energy level spiked back up. I felt normal. I felt like I could go out and do anything. So it really excites me that you're targeting, at least in the beginning, that range, because that's an area where we can manage our symptoms through diet, medication, lifestyle changes, and being more active, and hopefully not even realize that we have any kidney issues thanks to this device.
So let
Now,
me actually
okay,
bring something that may be interesting. So let's use an analogy that I think some of our audience would be familiar with, which is a pacemaker.
mm-hmm,
So if we go back 60, 70 years, right? If you had the conditions that required a pacemaker, you died, or if as pacemaker, the first pacemakers became available, you'd be hooked up to a machine the size of a refrigerator, and you would have to be walking around with that or be in the hospital with that big size
mm-hmm,
machine. Over the time, with technology improvements, today we have pacemakers this
tiny,
size, right? And they let you live like an almost normal life and
yeah.
do all the things you do. So we would envision a bioartificial kidney allowing that same kind of analogy for kidney patients.
Yep. Now let's say it was ready and I got one implanted. Are there any precautions that you foresee or any things that I wouldn't be able to do? Or will it pretty much be, once it heals, I'm normal as far as
Well,
being able to go out and do the things I want to do?
sure, sure. So anytime you have a medical device, you are always not absolutely normal, but that's okay, right? We can still take trips. We
Yeah,
can't do that
exactly.
always. Isn't it dialysis, right?
Taking trips
So
and not worrying about a dialysis center, being able to travel international. Can I probably eat a little more normal?
so people that receive the bioartificial kidney will be able to eat and drink freely, unlike dialysis patients who, as we all know, have severely restrained diets.
Mm-hmm.
The patients will not be immunosuppressed, so they will also have lower risk of infections than transplant patients, for example. So you can go swimming, presumably. I am sort of, but today with a
Yep.
dialysis patient, especially if you have a catheter, PD, that's a risk, right? You worry about infections because as in this day of the pandemic, as we have read and heard, if you're a kidney patient, especially if you're a dialysis patient, you're at a heightened risk of
Yes.
not only getting COVID, but also the bad effects that come with COVID. Why? It's because your body's immunosuppressed just
And
by
even those
having
who have
that
a
kidney.
transplant, a lot of them are very concerned about COVID because they're taking those drugs, which reduces their immune system.
Absolutely. So by avoiding the immunosuppression drugs, you actually are able to live a more normal life. And I think people will appreciate the ability to take trips, have not to worry about how much water they're drinking, and can not have to worry about phosphorus binders, eat cheese, eat pizza, have bananas, if you
Oh,
will. Those are the kinds of things one might be able to project. And this is not all fantasy. We actually know that for patients that have had more continuous therapy, when they've done dialysis for long periods of time, they're able to have more liberal diets, and that's we can gives us a basis to think about what an implantable bioartificial kidney might provide.
yeah. You'll make a lot of kidney patients happy because it's challenging to accept so much that we can't do or that's been kind of taken from us, like pizza or a nice big old ribeye steak or something like that. And being able to think of a day where I can enjoy that and not worry or have the next week where I just feel awful. Oh, that's awesome. Now, a question that was asked, it's a great one right here. When this is implanted, do we expect any issues with the body seeing it as a foreign object? Or is it just because of what it's made of, it'll be okay?
So the cells are protected and there's no immune reaction. So from that immune suppression perspective, that's addressed.
Hmm.
But like whether it's a pacemaker or orthopedic implant, it is a foreign body. So what the body
Yeah.
has to adapt to it. So using analogies from the cardiovascular world, say pacemaker, yes, you'll have a little pocket of tissue that forms around the bioartificial kidney. It does not interfere with it. It just is scar tissue that anytime you have, like in a pacemaker, a little pocket of tissue forms,
Yep.
and that actually helps hold it in place. So we would imagine we would have something like that. And yes, if you go to the you know the considerations for MRI imaging and the considerations for going to the airport scanners, but there's really not any other biological issue to worry about. But you'll also be monitored, right? You'll also be
Yep.
monitored to see if there's any other reactions, so that if there is, appropriate precautions and appropriate actions can be taken.
And are there any age limits expected for people who will be able to get one of these?
So it's a question we get, and I think from the engineering side, the answer is no. But remember, it's still going to require surgery.
Hmm.
And so that's going to probably have some bearing on being able to get this device. Now, we cannot at this point say what that's going to be. That's going to be probably decided by the ethics boards and by the individual patient's nephrologist and surgeon at the time.
Now, the cost. And people they're so eager to hear when this might be
Yeah.
ready. We're getting there, guys. We're getting there. That's the number one question on everyone's mind. We'll get there. How much do you anticipate this costing? And do you think it'll be something that insurance might cover or the government might cover, since it will replace the need for dialysis for many people?
So it's a very important point you bring up. In our country, the United States, dialysis is very expensive to the insurance company, and the primary insurance for dialysis is Medicare.
Hmm.
And it costs Medicare about $90,000 per dialysis patients per year. And it's not just the dialysis procedure, but all the complications that come with it and the medication. So when Medicare looks at a dialysis patient, they're estimating a dialysis patient $90,000 per year.
Yeah.
A transplant patient, after the transplant is put in, the maintenance cost of a transplant is about $30,000 a year. So think about the difference. So it's a lot less if you're able to get a transplant. So we know just from the engineering estimates, and these are still very early estimates because we're not in production and we do not know what the business situation is going to be. But we estimate that the device will cost no more than what it costs to maintain a transplant. And it will also depend on how fast, the economies of scale will allow us to bring the cost down. But let's just say it will be no more than the cost of a transplant once the device is manufactured at scale. And we do expect this device to be covered by insurance, and we'll hope to be working with Medicare to secure reimbursement coverage while the device is simultaneously undergoing the FDA review process. And to that point, there are actually incentives that are being discussed at Medicare about how to accelerate the development of breakthrough devices. And
Hmm.
one of the proposals we hope could become reality is that if you're a breakthrough device, you would get automatic Medicare coverage. So that would be an
Oh,
incentive to
that would be
insurance to
awesome.
take on.
Yeah. Now, what are some of the challenges you guys have had in your development that you have overcome?
Sure. So remember, this idea started off when Dr. Fizel approached me about 20 years ago and said, can you apply your engineering to help patients on dialysis? And it really started off from a conversation, and then it went to some back of the envelope calculations, and then we started working on to make it a reality. So to do that, we had to work through a number of issues. So
Hmm.
one of the technical tasks we had to take on was to build this new membrane technology. So conventional polymer dialyzer membranes, we quickly concluded, were not going to allow for an implanted system. So we looked at what was possible. So we came upon using semiconductor silicon, the same material to make electronics, to be able to make this new generation of membranes. And one of the challenges is this material is brittle. So the very first membranes we made had great transport capabilities, if you will, filtration, but they're very fragile. So through a combination of design refinements and material selection choices, we have refined the membranes such that now they survive pressures well above 30 psi, which is beyond anything that you see in the body. That was one challenge.
Yep.
Another challenge was blood clots. As anybody who knows, anything that touches blood can clot. People with stents, for example. That's a big issue. How is that addressed? Well, that's addressed by taking blood thinners. But blood thinners have very serious side effects. So another challenge we worked on was minimizing the likelihood of blood clots. Through a combination of improved coating chemistries and refining of the blood flow geometry, we're now able to operate the device prototypes without the need for blood thinning drugs like heparin. So we feel like those are two big challenges that people were very skeptical about addressing that we have addressed. And we've also been able to work with our partners who have taken cadaver kidneys, taken the cells out, and we can put them in our device. So these are challenges that we had to work through, but today we have overcome those challenges, and that's what gives me so much optimism about where we're headed.
Awesome. And speaking of where you're headed, what challenges lie ahead between now and getting this to market?
Sure. So I can see where you're eventually heading to. So I know you're getting all these
that's
other
the next
questions
question, everybody out there. It's the next one, the one you're all wanting. It's next.
Yeah. So this is how you get all the other information in. I see that. Okay.
Right. We get all the other information and we hold it and then we let them know.
Right. And I'm happy to be part of it, and I'll tell you everything I know. So let me start off by talking about the challenges ahead. So medical research, medical development is fundamentally a scientific effort. And sometimes it's based on discovery science. And let me use the analogy of, COVID-19. We have all these people working on a vaccine. It's not like it's, hey, we know everything there is, let's make a vaccine. They actually have to go experiments in test tubes. They got to look at stuff. And they do all these experiments and say, sometimes it's a matter of statistics. They have to do, a gazillion experiments to hit to, so statistically they can get to that one that works, right? So that's what I call discovery science. Luckily for us, we are actually not pursuing discovery science per se. Our work is fundamentally an engineering effort. So think of engineering as like, it's still hard. It's like building a rocket. It's very meticulous, but you're not waiting to make a discovery. You got to work hard. It's slow and time consuming, but you're going to get there. This engineering effort means that we now have the fundamental scientific knowledge to make the bioartificial kidney. And to date, we have shown successful demonstrations of miniature prototypes of the hemofilter and the bioreactor. To achieve our goal of a functional bioartificial kidney, we'll need to scale up these components into clinical size, integrate them together into a single device, and then demonstrate their successful operation, first in animals with non-functional kidneys, and then clinical trials. So let's talk about how we move forward. So likely challenges will revolve around the scaling up of membrane production and making sure we can get more cells for the bioreactor. Luckily, I think we can take advantage of something that's already out there. There's a strong manufacturing infrastructure for semiconductor electronics production. The same thing we're going to use to make our membranes. And we'll use that to scale up. For the bioreactor, I anticipate we'll leverage much of the experience with recent breakthroughs in cancer immunotherapy or regenerative medicine. Here, they're using cells to attack cancer. They're using other cells to grow tissues like bone and cartilage. And so we'll take advantage of those to apply to us. To ensure successful development, the other challenge, I think, which is important for the audience to appreciate, is we need resources and funding, right?
Yes, yes.
And
And has COVID been slowing that down, that funding?
Well, funding has always been a challenge, and COVID makes it even more challenging because that's another thing that people have to think about. I should say we've been lucky and we've received generous support from donors, small to large, foundations, and government agencies such as the National Institutes of Health, with grants that have totaled over $10 million over the last decade or more. But to complete the technical development of the prototype bioartificial kidney, we'll need about that much more, and then you'll also require additional money to bring it to the market through clinical trials, manufacturing, and distribution. So to provide some perspective, implanted medical devices typically take on the order of $50 to $100 million, depending on the complexity of the device, to complete development and clinical trials.
Yeah, what we need is someone like Apple to jump on board.
Or so Google or anybody else, right?
Yeah, there's so many that have that money. Oh, it would just be life-changing for so many people around the world. All right, now the big question that everyone has been asking and wants to know, what does it look like for the timeline for when this will be available for clinical trials, as well as when do you see it possibly being available as something that we could get?
Sure. I'm happy to answer that question. And that question comes up obviously here. It comes up in my emails. It comes up on social media. So let me start off by saying that this is a fundamentally engineering effort, and it is not a discovery science effort. Yeah, sure, there'll be some issues we'll have to work out too, but we're not waiting to make discoveries. So what is the expected timeline? I think is fundamentally what everybody wants to know.
Yep.
Once the technical development is complete, the device will need to undergo a series of clinical trials before it gets to the market. Now, without any unanticipated scientific or engineering challenges, our team has been thinking about this, and we have anticipated some, and there's some that we may not have anticipated, but let's assume we've anticipated most of them. Without any of these unanticipated challenges, the technical development can be wrapped up within a couple of years, assuming, and this is the part I think people should appreciate, assuming sufficient funding is available. We plan to work closely with the FDA through the Fast Track program and to go through the clinical trials. And if the clinical trials are successful, the bioartificial kidney will be commercially available within a decade, I think.
Fantastic. That's kind of what I was thinking. 8 to 10 years, hopefully get it out there. My doctors have told me if I stick with my diet, I've got at least a decade or more of my kidneys before I got to start worrying about anything. So hopefully this is ready. Now,
you bring up an important point, though. I think I should. Yep. So, which is, yes, people have gone into dialysis and beyond in transplant, but you can do something about slowing down the progression of kidney disease. So some of the people in your audience, it's not a hopeless cause. You can take some of the steps you yourself have taken to slow that down. And I want to stress that, yes, I am working on something that treats kidney failure, but just as important is things patients and their families can do to slow down the progression of kidney disease, and we should always pay attention to that.
Yeah, and I'm hoping we'll see more education on preventive things that people can do a bigger push for using renal dietitians, taking action earlier. Because a lot of doctors, they seem to wait until your GFR is 30 or below. It's kind of the old school way. And I'm hoping to see a change. I am starting to see it where doctors are starting to get more involved at GFRs below 60, saying, hey, let's look at your diet. Let's be a little bit healthier. Let's cut back on the ibuprofen.
Right. And it's important. I mean, just the same, again, this is not news to much of the audience. The same things that we all hear: go do exercise, control the amount of salt, amount of sugar. Those things all are important. And I think, you have to think of it in terms of a healthy lifestyle to arrest that. And if those fail and you end up needing dialysis or artificial kidney or a transplant, then obviously those are there. But we know just the growth in this population, a lot of this is being driven just because of hypertension and diabetes. And those are things people can do something about. And I encourage everybody to do their part for that.
Yep. Now, what can we do to raise it? Because this is big news to us. So what can we do, the kidney community, to help raise awareness and to help generate more of those funds that are needed to make this a reality?
I appreciate that. And I think the first thing I think we should make sure is people know that we are working on a project like this, because I think you hit on this very early. It's about hope. And I think it's so important that people know that it is conceivable that there's something that can help patients who are on dialysis and are very low, if you will, or unlikely to get a transplant, right? So
Yep.
I would say, first of all, have the audience and everybody for that matter tell their friends and family about the kidney project and what we are trying to do. Encourage them to donate. Every bit helps if they're in a position to do so. Whether it's a small amount, a large amount, we use that money to directly support our research and development activities. If that's not possible directly, think about conducting crowdfunding. Through the UCSF system, there's a way to get a crowdfunding campaign going, and all that money goes into the development effort. And it can be as simple as, hey, let's get together and we'll put an awareness out around a specific person or specific city and do that. If you know of some mission-oriented investors that want to make a difference in humanity, please tell them about what you're doing and say, hey, you get a chance to work on the first ever implantable artificial kidney project. And finally, I'll say, have all the people in this country consider calling or writing to their congressional representatives and ask them to support policies that will encourage funding and support that is necessary to make the bioartificial kidney real.
Yeah, and that is definitely something you'll be seeing me do. I'm going to spread the word as much as possible, reach out to everyone that I know that, can help spread the word and reach out to my Congress people. This is something we just so badly need. And it's awesome to hear that it's not a technical problem or an engineering problem. You've solved so many of those hurdles, and that it really is a funding issue right now. And hopefully we can help.
Yeah, so let me just say that. That's actually I'm glad you mentioned that, because people have come to me and say, why aren't you doing this faster? And sadly, the pace of our progress is being held up by the amount of financial resources that are available. This is different from discovery science, where you have a lot of this, you're just waiting for the discovery to happen.
Yeah, you're waiting for it to happen. You never know.
Exactly. Yeah, it's a matter of like, here's what's rolling. So you put it very clearly. To the extent we can solve that problem, it just makes the project go that much faster.
Yep. Awesome. Now, for those, a few people have said, hey, how can I donate? What is your website for the kidney project?
Sure. So our website is kidney.ucsf.edu. It will take you to the university website. There's a link there that takes you into the donation page that goes to the university, and then the university then directs the funds to us, and it's a tax deductible donation. and you'll get a receipt that you can use for your IRS purposes. We are appreciative of anybody who wants to do a crowdfunding campaign. Also, you can reach us through that website, and there's a way to launch your own crowdfunding through the UCSF, and you get to control that. You get to say what you want to do, who you want it to go to, and then people raise money, and that money after you've done the campaign will come to us.
Well, I'm going to definitely follow up with you on that. We're going to get that started here so that our community and everyone that we reach can be aware of it and hopefully join in what they can to help make this a reality sooner than later. Now, before we go, because we are getting close to the top of the hour, and I don't know if you have something right after this or not on your schedule, what is the iHemo? I read a little bit about that, and it sounded like it was leveraging some of this technology that you've developed to make dialysis at home even better.
Sure. So it's a great question. I'm getting that a lot. So what is the iHemo? So the iHemo is a system that will allow patients to perform hemodialysis conveniently and safely at home. So it's a home hemodialysis system. It's not a bioartificial kidney, but there are some similarities. The iHemo shares the same technology as the bioartificial kidney's hemofilter unit, meaning the silicon membranes to remove toxins from blood. While the bioartificial kidney also uses cells to provide the key functions of the natural kidney, the iHemo does not use any cells. We see the iHemo as a stepping stone to the bioartificial kidney because it allows us to develop the membrane technology and test it out, for therapeutic purposes.
And how close is the iHemo to being available?
Sure. So just to talk about to finish up, give you a little more insight in the iHemo. So the iHemo, you still have the hemofilter of the bioartificial kidney that's going to be used as a biocompatible dialyzer. So this filter unit is going to be surgically implanted inside the patient's abdomen. The device connects to the blood vessels on one side, creating a permanent blood circuit inside the body, and on the other side to catheters that lead to an external bedside pump unit. The patient's heart pumps the blood through the implanted dialyzer, while the external pump circulates dialysate and carries away the toxins and excess water. So you see the similarities between the filter in the bioartificial kidney and the filter in the dialyzer, except there's no cells. From the viewpoint of patients, it simplifies the dialysis procedure because there's no need to cannulate with needles, and instead it offers a simple through the skin connection to connect to the dialysis pump. So what is the anticipated availability is we have to develop this technology. So currently we're looking for partners to help support the development and commercialization of iHemo. Because it does not use cells, the iHemo can get to patients faster than the bioartificial kidney, likely within 5 years or less.
Oh, that would be awesome. And from what I saw in my research, it's a much smaller unit than the current home units and far less complicated.
That's right. It's going to look, from the viewpoint of patients, similar to a PD system on the outside, but allow you to do home hemodialysis. Now, multiple studies have shown that more frequent and longer dialysis sessions can significantly improve the health, survival, and quality of life. So the user-friendly patient interface of iHemo will make it easy for patients to obtain these benefits.
And I'm guessing since they can do it longer at home, it's probably less stress on their heart.
That's exactly right. So there's actually some very exciting data that initially in Canada, now more recently in the US, that shows that if you can do dialysis, for example, 6 nights a week, 8 hours a night while you sleep, these patients not only feel better, but they need less EPO. They can eat and drink more freely. They sleep better, Yeah, and there is
Oh,
a whole bunch of benefits that come about with it. But the infrastructure for doing home hemodialysis for those long periods of time is tough. You got to not only cannulate, you got to make sure there's no accidental disconnect, and there's a fancy machine to control the blood pump. This avoids all that and makes hemodialysis so much simpler. So you can do nocturnal hemodialysis and get these benefits, presumably.
awesome. Well, we're at the top of the hour. I want to thank you so much for taking the time to share the work that you've done, and thank you for all that you have done. It definitely is bringing hope. I see a lot of positive message. People are very excited. We're going to work on raising awareness and do what we can to help raise funding for this. And wow, I'm just so excited.
Thank you. I encourage you and your audience to follow us on Facebook.
Yep.
And we are also active on social media. Please join us there. We use the Facebook and social media to provide updates. And the moment we have any news on the timeline, other technical developments, we'll certainly share it with this community.
Awesome. And I've put links to both your website and your Facebook in the description on YouTube. So anyone out there, if you want the links, go to this video on YouTube. We're also streaming to Twitch and Facebook, but go to YouTube and the links are there in the description. Thank you so much. And I'm sure we'll be checking up on this again in the very near future, once we get some more progress made. And wow, this has just been so exciting. People are so excited over here. Show you some of the messages.
Thank you. And
the chat
again,
is
a big
full of thanks.
Yeah. No, I see a lot of thanks to me, but really thank you, and thank you to the community for inspiring and encouraging us. It means so much to us to hear the supportive words, and we understand the frustration is not going faster. I hope I have been able to explain some of that, but
Oh,
please
yes, you
know
have.
we are committed and we're going to get this done together.
Awesome. Thank you very much. And everybody else out there, I'll see you in the next video. Bye.